Okay, everybody. So now moving on to chapter 8, part 2. And we're going to be focusing on evaluating association claims. So somebody makes an association claim such as this. Children with autism are better at solving mathematical equations. If I'm interrogating this claim, I'm asking several things. So this would be an example of an association claim. One thing to ask yourself when evaluating if it's an association claim is ask yourself, can you imagine them manipulating the experiences in that claim? Here, autism. Now that one's difficult to imagine that you can assign people to be on the autism spectrum or not, right? That really can't happen. That's not practical. That's not possible. The mathematical equations part, right? That one, let me switch to the pointer, might be, you could probably imagine people being assigned to different math conditions, but let's say I give you more detail and said, well, we just had people do a math test. Well, if that's what they're doing, then that was also a measured variable, right? This was likely measured, not assigned. This was likely measured, not assigned. If you can't imagine people being assigned to a condition in a variable, then it's likely not a causal claim. It's likely an association claim. So just to review really quickly what a moderator is. A moderator is something that you've taken into account in your study. You've taken this into account and you're interested in seeing how the IV causes the DV or is related to the DV, right, is associated with the DV. And you've thought ahead and you've realized, well, there might be a moderating variable that might influence this relationship. So for example, you might be looking at caffeine and anxiety. Whoop, excuse me, let me go back. There you go. And anxiety. And you might have thought ahead and thought, okay, well, maybe the sex of the participant may influence this relationship. Maybe the strength of the relationship between caffeine and anxiety might vary based on being male or female. But let's say maybe you think time. Maybe the impact of caffeine on anxiety might vary by time of day, right? So you have some people do it in the morning, some people do it in the afternoon, and you find that exactly that, right? So when you're thinking of a moderator, that's what you're looking at. Whereas a third variable, which would be something like this, is an alternate explanation to the relationship you've observed between your variables of interest. So let's say you have caffeine and anxiety, and you find there's a relationship there, right? You find that, okay, it seems like these two are related. People who drink more caffeine tend to be more anxious. So in this case, that would be an association claim, right? People who drink more caffeine tend to be more anxious. Well, is there any alternate explanation to this? Well, maybe people who drink more caffeine, I don't know, have less sleep. So maybe anxiety is tied to the amount of sleep you're not getting rather than caffeine, right? So any alternate explanation to what you're observing, what you're claiming, like in this example, that would be a third variable, that would be a confound. Whereas here, in this example above, you've actually worked this other variable into your study design. So keep that in mind. Let me give you an example of this in the next slide. Okay, so in this example, I'm looking at the relationship between caffeine and anxiety again. And I thought, okay, I thought ahead. I'm like, okay, gender, or I should say sex. Sex of the participant may influence the impact of caffeine on anxiety. So here you have the sex of the participant. Here you have the caffeine condition. So in this case, I did have control over this variable. I assigned some people to decaf, some people to caffeine. And these scores are my measures for anxiety, right? So I do think there's a relationship, but I think it might vary based on gender. These are 3 potential outcomes. In this outcome, it looks like for male participants, there's an increase in anxiety, or there from decaf to the caffeine, or there's an increase of about 20 for the people who took the caffeine versus the control condition. Whereas for female participants, there is no difference. So you might find this, right? You might find that for male participants, there is an impact on anxiety, whereas for female participants, it doesn't look like there is. Let's look at this example now. So in this example, you find that, there seems to be an increase of an anxiety or for the caffeine group compared to the control group. But then, surprisingly, for the female participants, there's a decrease in anxiety, right? So that would be a surprising finding, but maybe there's a opposite effect for female participants. So there might be a positive relationship here and a negative relationship here, which is fine. That can happen. This would still be a moderating variable, right? This would still be important to observe. Okay, the impact is less for one group and not there for the other group, or strong for one group, negative for the other group, or here, even if it was a lesser impact, let's say this was 70, that would still matter. The relationship between caffeine and anxiety for men is stronger. It's still there for female participants, but a little weaker, right? If I use that example of 70. But now let's look at this example. So now you have caffeine, gender, sex again, and we find that it's about a 5-point increase for the caffeine group in comparison to the decaf groups, and that's the same for male and female participants. Now, whether that's significant or not, we don't know. We don't have the p-value here, but it's the same for both participants. There's no moderating variable, right? Maybe you include this to check. You find, no, there seems to be a direct relationship between caffeine intake and anxiety, and it doesn't depend on gender. It doesn't vary based on the group membership for sex, not gender. Let's go on to the next slide. And now moving on to interrogating social claims. Give me a second. So when we're interrogating association claims, we're focusing on construct. Did they measure what they actually said they were measuring? Statistical validity. Statistically speaking, are they supported in their findings? And external validity. Can they generalize their findings to the population of interest? Internal validity is kind of what we sacrifice if we're using this approach. If we're looking at association claims, if we're doing bivariate correlations, we don't really have the support to make the claim that we have strong internal validity if we're not manipulating a variable. So we're not going to focus on that as much, but I will explain how this relates to how this still relates to bivariate correlations. Again, association claims. So just to clarify and to remind you all, a bivariate correlation it's a type of association claim you can make. If you claim that one variable, that one variable is related to another variable, that's a bivariate correlation because you're focusing on two variables, but it's also an association claim because you're not manipulating either variable, right? You're just measuring X and you're measuring Y. You're measuring both variables. Okay. So construct validity, just as a reminder, is focusing on are they actually measuring what they said they measured. So let's go over this example. We have mindset that was developed by Carol Dweck, currently at Stanford, and she developed her mindset scale to measure this. So if we go to the next slide, we have two aspects of growth mindset. You have growth and you have fixed, right? So when we're looking at this, we have to say, okay, what actually is this concept, this construct that she's calling mindset. How did she measure it? Growth mindset has to do with the idea that you see learning and skills as something that can grow over time, with practice, with experience, like a muscle. Fixed, that's you're just good at that or you're bad at that. You're not going to get any better. You're not going to get any worse. You have a fixed view of skills and ability. For example, you might hear people saying things like, well, I'm just not good at tech. I'm just a good writer. I could write an essay the day before and I'll get a B, I'll get an A. That both those examples are fixed. I'm just good, I'm just bad. So if you're evaluating this this measurement and the validity in terms of, whoops, actually went forward. Sorry. Why is it going forward? Okay, give me a second. Okay, okay, so I'll try to work on that. But if I'm evaluating the construct validity, I'm asking exactly that. How did she measure? Well, how did they measure? Are they actually measuring what they said they measured? Here's some things to ask. Well, do they have good reliability? Right? Can I implement this measurement? And will a person who showed up as having a growth mindset in the first measure repeatedly show as a person with growth mindset? If they move between these two, right, and each time you measure them, then there's some issue with your measurement. Is it actually measuring? Is this measure of mindset actually measuring what it says it measured and what it was intended to measure, right? And then you have all these other aspects of validity we can take into account. Face validity, does it look good? Convergent validity and discriminant validity. Remember, that has to do with how does it match up with scales that measure different things? Does it actually look similar? Does it correlate with other scales that are measuring a similar thing? Does it discriminate from other scales? It shouldn't be similar to scales that are measuring related but different concepts, right? But mainly, the main thing to remember is just remembering, is it actually measuring what it said it's measuring, and how well is it measuring that one thing? Now, in terms of statistical validity, we want to make sure we take into account, are the claims being made, are they supported by the data, right? So here are some questions we're going to review. What is this effect size? And remember, the effect size is a relationship between the two variables. Is it a strong relationship? Is it a weak relationship? And are they representing that correctly, right? Are they saying it's a strong relationship when it's a weak relationship? Then that's an issue. And then here, statistically speaking, is it significant? Is it less than 0.05? Could there be any outliers that are impacting the strength of the correlation? Is there restriction of range? We'll go over that in the next few slides. And is the association actually curvilinear, right? So let's go ahead and review what these are. When we're dealing with effect size, I would say this is equally as important or more important than the significance level, right? So we talk about the p-value, we talk about significance, we talk about p being less than 0.05, and you do need that because of the standards we set in psychology. But in addition to that, what you want to ask is, well, how strongly are these variables related to each other? So in this situation, y and x, if I asked you, well, what is the effect size in this bivariate correlation? I'm asking you, well, how strongly is y correlated with x? What is the strength of that relationship? Right, so keep that in mind. Effect size, strength of the relationship. In bivariate correlations, we use the R coefficient. So that is our effect size. So it kind of works out. you know this, right? You've learned that, okay, this shows how strongly they're related. We want something that's closer to 1, 0.8, 0.9. That's great. That says that these are strongly correlated. Same idea. If they're strongly correlated, if that you have a strong R coefficient, then you have a strong effect size, a large effect size. Make sure to look at that table that I gave you in this chapter that reviews the different strengths, keeping in mind that we use different criteria because we're dealing with people, and there's so many variables that we're dealing with that it is going to be difficult to get a correlation this high in the social sciences. But when you're looking at a scatter plot, keep this in mind. Evaluate the central tendency, right? I've been saying it more in terms of what does it look like a line? Is it easy to tell the direction? The closer it is to looking like a line, the stronger the central tendency, right? The stronger the effect size. If it's spread out like this, then the weaker the effect size. Here I'm going to guess maybe it's a point, well, actually it would be positive. 0.7, maybe 0.8. Here, maybe 0.6, maybe less, right? Actually, if this is 0.6, if this is 0.6, then actually it probably would be weaker than that. Sorry about that. Maybe more like 0.5, right? It's probably closer to 0.8. So if you see a problem like this on the exam, for example, and you see that one looks closer to looking like a line, has stronger central tendency, then it likely has a stronger effect size than something like this, right? And remember, when I'm saying effect size, you should be thinking this correlation value, or what I'm calling the R coefficient. Is what you should be thinking of. When we're dealing with effect size, again, we're thinking about, well, how strong is the relationship? If we do have a strong effect size, then we can make better predictions. So keep that in mind. Larger effect size, better prediction. So just to give you kind of a reminder, actually that's there you go. So here, again, looks more like a line. Stronger effect size when compared to this, right? Better central tendency, not as good central tendency. So this one, right? This one here on the top, in comparison to the bottom one, has a stronger effect size, and because of that, you can make better predictions based on this data. So here, this is data we've already collected, or these researchers have already collected, but now that we know there's a relationship between these two variables, height at age 2, height at age 18, then we can use this data to make predictions for other people. So next time at the doctor, they might ask a family of a 2-year-old, okay, well, let's measure their height, get the height measurement, and make a reasonable prediction of how tall they'll be at 18. This one on the bottom, the scatter plot, does find that there's a relationship between mother's height and height of their child, right? In this case, son. Because, genetics, there is going to be a connection. But it's not as strong of a relationship, not as strong of a predictor. So we care about effect size because it tells us the strength of a relationship, and in bivariate correlations or association claims, it lets us make better predictions. Let me go back into presenter mode. So you also want to consider, is a correlation statistically significant? Now, we have all of this here, which, is important to know, right? You should know the technicalities behind what a p-value means, what does it mean to be statistically significant, but make sure you can differentiate between this and effect size. Effect size is the strength of the relationship between the two variables. If you're thinking about like comparing two different groups and you're wondering if they're different, effect size in that situation tells you that the amount of difference, how big is the difference. Statistical significance only tells us, is there a difference? Or in the case of association claims, is there a relationship? So actually, let me go back to the previous slide if I could figure this out. Yeah, great. So both of these might be statistically significant. They probably were. The thing is, well, okay, this is statistically significant. Let's say you only did this study, and I told you that. Great, that sounds good. But you don't know the strength of the relationship. So don't settle for just knowing is it statistically significant. You want to know what is the effect size. But let me actually go to the next slide. And just to be as straightforward as possible, we're just asking, is it below? Actually, yeah, there you go. Is it just below 0.05? That's essentially what we're asking. Is there a less than 5% chance that you found that relationship between the two variables when it actually didn't exist? Right? We're trying to reduce the situations where you might find a relationship there between your two variables, but it actually doesn't exist. If you had a p equals 0.06, it is not significant according to our standards. But what this means is there's a 6% chance that your findings are due to some error. 6% chance, right? So think about that. 5% versus 6% chance. Would you be okay with a 6% chance? Actually, maybe you might, but it doesn't matter because we've set our criteria at 0.05. Okay, I guess it's my cue to move on. So keep that in mind, that we've chosen that value as a field, even though you might think 6% doesn't sound that bad, or even 5. Like, why should we throw not published data that's 5.1%? Well, we set the criteria. It has to be below 0.05. Let me actually go back a slide. No, it's taking me forward. Okay, there you go. Okay, so now a fourth thing to keep in mind is, well, are there any issues with restriction of range? When we're dealing with restriction of range, what we're dealing with is missing data. Well, taking this for example, here we have an effect size or correlation coefficient of 0.33. According to our criteria, that would be about a medium effect size. Doesn't seem bad, right? And we're looking at how SAT scores are correlated with GPA. So pretty much you're trying to see, well, if I know a student's GPA, actually, other way around. If I know the student's SAT score, can I make a reasonable prediction about how they'll do in college in terms of their GPA? Here, it looks like we have a medium effect size, right? 0.33. But you can notice here, we're missing students who scored between 1,000 and 1,800. Now, keeping in mind that this was the old way of scoring the SAT score, it's different now. But we have people who are missing from about the 50th percentile and below. So why is this an issue? Well, let me show you what happens when you include the entire group. So when you include people who are between these SAT scores, we find actually it is a very good predictor of SAT score. I mean, the SAT score is a very good predictor of GPA. It's actually stronger than we had originally thought. So keep in mind, when we're evaluating validity, we're not just looking at, well, did they find something when there really isn't a relationship? We're also thinking about, well, are they misrepresenting or getting a false reading on the actual relationship? Here we find, well, it's actually stronger than initially published when we include a full range of the data set, right? Why might that happen? Well, maybe initially when they only had this range, they were recruiting participants from higher economic brackets, students who had tutors, students that were able to take SAT score, SAT classes. And then they broadened their search to include participants that were lower income, had less access to these resources or different schools. And you got a full range of participants in terms of their SAT score range, right? So we want to make sure they have a full range of participants in their study. Now, excuse me, I have to take a drink of water. So when we're dealing with associations, we focus mostly on positive and negative correlations, right? Well, these aren't the only kind. You might have a curvilinear association, and that's something to consider, right? Do they have the full range of data? If not, if they think there isn't a relationship or there is a relationship, you have to take this into consideration. Might there be a curvilinear relationship? Here in this example, you have age in years on the x-axis, use of healthcare system on the y-axis, right? So for example, let's say they only had this age group from birth to 20. Well, it looks like use of the healthcare system is actually going down. But then let's say they included let's say some researchers only did it with older groups, and it looks like it's going up in general. To get a full picture, you need to have the full age group. Okay, there's no eraser, so let me undo that. But then what they find is actually it's not positive or negative, it's curvilinear. You find that early on, there's more use of the healthcare system. And for those of you who are around children, who have your own children, you'll relate to this. You're going to the doctor, you're making sure your child's eating, they're doing checkups, they're making sure that the child has has had their immunization shots, is getting weighed, is gaining weight. You're doing all of that at the very beginning. So there's many doctor visits. But then around this age, people tend to be healthier, need to visit the doctor less. So you see that happening. But then as we get older, we start having more healthcare issues due to aging, and you see that increasing again, right? So it starts high, goes low, then goes up again, right? So this is something you want to check into, because if they only have a piece of the data, they might think it's a positive. And in this case too, if they only have a piece of the data for early age groups, they might think it's negative. But when you have the full picture, you realize it's neither, it's curvilinear, right? So that's something to ask yourself. For this type of association claim, I would describe something like this, then ask you what type of association correlation are we dealing with? Is it positive? Is it negative? Is it curvilinear? So keep that in mind. Now, you want to also think about external validity, meaning can we generalize our findings from our population of interest, from our sample to the population of interest, right? So these are the people we recruited for our study. Can we apply what we found with this sample to everybody here? Now, it depends on many things, but specifically, we have to consider, well, who were the participants? Did the researchers do a good job of recruiting a good sample, a representative sample of the population of interest? Did all genders, all ages, all ethnicities, all income groups get included in sampling? And how were they selected? Not only did they do a good job of getting people from different backgrounds, different demographics, different income brackets, but we also care, did they use random sampling, right? If they did that, then likely they have good external validity. If they didn't, then we might have an issue. So for example, here you have people who are gray, red, orange, and blue, and you notice that my sample only has blue people, I might not be able to generalize my findings from my study to the population of interest, meaning I have poor external validity. So keep that in mind when we're assessing external validity. We're asking, how did they recruit their sample? So, okay, so we're gonna go over why we don't care about internal validity as much in these type of studies, or association claims, right? Mostly the examples I've been giving you are bivariate correlations, but just in general, when we have association claims and we're evaluating the validities, we generally don't emphasize internal validity because we just know it's going to be poor. Okay, so let me give you an example, a reminder of what a bivariate correlation looks like, an association claim, a type of association claim. Here you have couples and how they met, online or offline, and we have a measure of, well, how satisfied are they with their spouse, right, and their marriage. So when you're assessing whether it's an association claim or a causal claim, you have to think, well, based on this study description, did they assign or did they simply recruit people who were already in groups or just measure the variables of interest? Here, marital satisfaction, think that through. Can you think of a situation where they assigned people to be satisfied or dissatisfied? That would be hard to imagine, actually probably not ethical. So here, probably measured, not assigned, not manipulated. What about this one? Can you imagine a situation where they assign people to meet online or offline? Now that's not probable, probably not likely, would be unethical. So most likely they were just asking, right? So you want to asked for that information. Well, how did you recruit these people? Had they already met each other online, or did you get them to meet each other online? In this case, in this study, they recruited people who met online or met offline, right? They already had met each other through these means, so you know that's measured, right? For it to be a manipulated variable, they would have to have assigned people to meet somebody online or offline and then marry them, right? That would be part of the study. That's not ethical, but that could be done, right? So you do want to look into the details, but if you wanted to make it a true experiment, it would have to be that extreme. You would have to have people meet, kind of laughing because I can't imagine that happening, but you'd have to have people meet online and then marry that person, or people meet offline and then marry that person for it to be manipulated. If you're only recruiting people who already met online or offline, it is just measured. Okay, so when we're asking about internal validity, we're asking about one aspect of the criteria for causation, right? So let me walk you through the criteria for causation, and then I'll get to internal validity. So to be able to claim one variable, the IV caused the DV, and is not just related, you have to establish covariance. You have to establish that as one changes, the other changes. Now, it could be this, right? They both go up together, or one goes up, the other one goes down, right? A positive or negative correlation. So keep that in mind. You have to establish that as one changes, the other changes. You also have to establish that the IV happened before the DV. So you would have to say the IV came and then the DV happened. Now in this example it has a question mark because, well, let's say there was a situation where you can't establish which one happened first. If you can't establish which one happened first, you cannot claim causation. Finally, this final criteria, internal validity. We have to establish that there is no third variable problem. that there is no third variable that can explain this relationship. So for example, early on in the semester, somebody shared the example regarding wet hair leading to getting sick, right? This is something that people talk about in different communities. If you go to sleep with wet hair, or even if you go outside with wet hair, you'll get sick, right? Wet hair, sick. But if I can come up with any alternate explanation, then you have poor internal validity. You cannot establish that there's no alternate explanation. For example, I might say, well, maybe it's just that people remember the times they went to sleep with wet hair and they got sick, and they don't remember the times they went to sleep with wet hair and did not get sick. So I don't know, maybe it's memory. Maybe they were already sick, right? Maybe they already had the bacteria and then they got sick, and it has nothing to do with this wet hair, right? So any alternate explanation I could provide is an issue with poor internal validity. In bivariate correlations, because we cannot manipulate both variables, because we have poor control over the experimental conditions, we cannot rule this out, right? We would want to rule it out, but we can't. Because we can't rule out a third variable issue, we cannot claim we have good internal validity. So in association claims, it's just assumed that you have poor internal validity. Again, in association claims, you can satisfy this requirement for causation. You can establish covariation. You can establish temporal precedence, right? A came before B. You can establish that. Again, covariation. As A went up, B went up. You can say that, right? More sleep, better grades. Sleep came before grades. But then in terms of internal validity, well, in that example, well, was it really sleep or grades? Did me getting better grades give me more time to sleep? Is there some other variable? For example, maybe income? Maybe people who get more sleep also have more income because they don't have to work, right? So you can't rule out this third variable most of the time in bivariate correlations. Because of that, you cannot have good internal validity. You always have issues with internal validity when dealing with association claims. So that's my last slide. If you have questions, please let me know. I'll probably post the poll everywhere soon, but please do respond with any questions you have about anything I've reviewed here, and I'll review those in a future PowerPoint.